trig equations. And your textbook has two sections devoted to trig equations. Part 1, Part 2. Part 1, Fisher-Price problems. Part 2, not so Fisher-Price problems. We're only going to take a look at a couple of the easy ones today, and then we're not going to worry about the harder ones until we come back from break, because you'll forget some of this stuff over break, and I don't want to have to reteach a lot of stuff. So we're only going to do a couple problems, and then we're done. Two things, right? You have Chapter 5 homework due Sunday, and the next time I see you, is there an exam or not? Do we just have a Chapter 5 test, or is it 5 and 6?
5 and 6.
So you're good for a while then. Okay, good for a while then. The title, what's that?
I just had the multiple choice again.
Title of this problem is sometimes you can treat trig equations just like linear equations. And, unlike verifying identities. Verifying identities, you are not allowed to add, subtract, multiply, divide both sides by stuff. You're trying to transform one side into the other. Here with solving equations, now you're allowed to do all that stuff you could before. Add, subtract, multiply, divide, take square root of both sides, distributive property. All of that stuff you can now use. So we want to try to get sine theta all by itself. So if we start with 2 sine theta minus 1 equals 0, and we want to get the sine theta part all by itself, think of sine theta as being like x. If this was 2x minus 1 equals 0, how do you get x by itself? Well, we'll add 1 to both sides, and we'll divide both sides by 2. Okay? And here's where you need to seriously pay attention to the problem. They want all solutions that are in this interval. All solutions that are in this interval. So we get down here and we say, okay, what angle has a sine of positive 1/2? Well, what's the quadrant 1 angle? No. 30. What other quadrant is sine positive?
Will be second.
Quadrant 2 with a 30-degree reference angle gives us 150. So there are my 2 answers to this question. Those two angles are in this interval, right? And satisfy the equation. All right, see how we're going to do this? Keep on going, keep on going. Try the next one. Solve that for x. Solve by factoring. And you all know that to solve by factoring, you set it equal to 0. So let's subtract sine x from both sides. Who cares if sine x is 0? I'm allowed to subtract 0. I can't divide by 0. So if we look at it now in terms of sine x, tan x minus sine x is equal to 0. Now we can factor out a sine x. And we get sine x times the quantity, tan x minus 1 equals 0. What do you guys remember about the zero product property? Remember back when solving quadratics? If you solved, or let's just say you factored a quadratic and you had it down to x minus 2 times x plus 3 equals 0. Right? What does this mean? This means either x minus 2 has to equal 0 or x plus 3 equals 0, right? The zero product property. That's what you're going to use here. You currently have the fact that you got these two things that you're multiplying together and it's giving you 0. So either sine x is equal to 0 or tan x minus 1 equals 0. And we'll solve each of those independently. In the interval 0 to 360, what angles have a sine of 0?
Can you read it? 90.
0 and 180.
0 and 180, two of them. So this equation gives you two answers. X is 0 or 180. That equation gives you two answers. Now we answer the second equation. Tan x minus 1 is 0 implies that the tangent of x equals positive 1. And what angles have a tangent of positive 1? 45. And where else is tangent positive? Quadrant 3, good. 3. And I got to take 180 degrees, add on to it 45 degrees. What is that? 225. So folks, this equation has 4 solutions. Those 4 make the original equation true. One more problem, and we'll call it a day. And we said with this problem, compare this is a quadratic equation. Compare it with x squared plus x minus 2 equals 0. X squared plus x minus 2, you know, can be factored. X plus 2 minus 1, right? So our equation can be factored as tan x plus 2 times tan x minus 1 is 0. And right, if you FOIL that, we get the original problem. Tan x times tan x, tan squared. Outside, inside terms give me positive 1 tan x, and positive 2 times negative 1 gives me negative 2. So now we'll set each factor equal to 0. We have tan x plus 2 equals 0, and tan x minus 1 equals 0. This would imply that the tangent of x is equal to negative 2. This one would imply that the tangent of x is equal to positive 1. Let's do the easy one first, right? What angle has a tangent of 1? Pi over 4. But I need 2 of them, right? Again, it would be quadrant 1 and quadrant 3. So this bottom equation gives us 2 answers. Pi over 4, and also the quadrant 3 version would be 5 pi over 4. How about the one above that? What angle has a tangent of negative 2? What angle has a tangent of negative 2? It's probably one of our special angles. How about inverse tangent negative 2? Maybe not. Maybe then that one wouldn't be an exact answer. Let me put my calculator back into radians momentarily. Let's go back to mode. Let's go down here to radians. And now we'll say calculator inverse tangent negative 2. Oh. What did I do wrong? Got double parentheses. So this angle would be inverse tan something negative. That's quadrant 4, right? Inverse tangent being something negative that you're taking inverse tangent of. This answer that you're getting is the quadrant 4 answer in radians. So it's saying negative, 1.1 radians. So the whole circle has 2 pi radians. So we'd have to say, calculator, what is 2 pi? 2 pi radians. I need to go back 1.1 so many radians minus 1.10715. We'll stop there. So there would be one solution, 5.176 radians. Now you can see why they specified answer in radians. How about the other one? Is there another one? Well, I got inverse tan negative 2. Is there only 3 answers? Inverse tan negative 2. I got 5.17 radians. Where else would the tangent be negative? Quadrant 2. So we'd have to also take pi, quadrant 2 angle, and go back a reference angle of 1 point, same thing, number of radians, giving us 2.03.
Is that negative? No.
Nope.
No. Yeah.
Positive. Why? It's because of this word right here. All. Notice they are not saying, only give me answers from 0 to 360. Only give me answers from 0 to... No, they want all of them. And do you know how many that there are? An infinite number of them. So we have to write that somehow. We're going to save that problem to the end. The last 2 examples, we're back to specifying a range of values. So let's take care of these 2, then we'll go back and address the earlier problem.
Wow, quadratic.
This problem says, solve the following for x. We have tan x plus square root of 3 equals secant x. Square both sides. Now, why would we want to do this? You know why? It's going to create what? It's going to create some tangent squareds. It's going to be creating some secant squareds.
I thought you had to isolate the radical before you could do that.
Oh no. You can square both sides. It's just a binomial on the left. You're saying, would it make it easier if we took the root 3 to the right and secant x to the left? Is that what you want to try?
No, I just thought there was a rule with radicals that you have to isolate it.
That's if the variable was under the radical. You're thinking of back when we were solving equations like there, where you'd want to isolate the radical and then square both sides. That's exactly what you're thinking of. But you make a good point. Maybe we should flip-flop these terms around first. You know, let's maybe write this problem before we square both sides. No, we better not. Let's leave it the way that it was. Now, I'll tell you why I'm thinking ahead. Let's leave it the way that it was and square both sides. Because if I would bring secant x to the left and go ahead and square both sides, we're going to end up with like 2 tan x secant x. And I can't do anything with those 2. Whereas the way that it is right now, if I square both sides, I'm not going to have secant x, I'm going to have secant squared x. And we know there's a relationship between secant squared and tangent squared, right? We'll be able to convert everything to the same thing. So squaring the left-hand side would give us tan squared x, square the first term, multiply the 2 together and double it. That would give us positive 2 root 3 tan x. Square the positive root 3 gives us positive 3. And on the right-hand side, we would get secant squared x. Now, use your identity. Right-hand side of the equation.
I can choose square.
Give me a second here. When you square a binomial, you square the first term,
Yeah.
you square this term, you multiply the 2 together and double it. You end up with a positive root 3 tan x, another positive root 3 tan x. Secant squared is the same thing as what? Anybody look that up quick? Secant squared is the same thing as... No. No, in terms of tangent squared. Tangent squared plus 1. Tangent squared x plus 1. And look at that. Cancel, cancel. That's what I'm talking about. So now we have it down to 2 root 3 tan x equals, subtract 3 to the other side, negative 2. Divide both sides by 2 root 3. We have tan x is now equal to negative 2 over 2 root 3, so that's negative 1 over root 3, which is negative root 3 over 3. So this question got easy looking rapidly. So what quadrants is the tangent negative? 2 and 4. And what angle, what would be our reference angle, has a tangent of root 3 over 3?
30.
Is it 30 or is it 60?
30.
30. And do we want degrees or radians with this problem? Radians. So we're looking at pi over 6. We're looking at pi over 6 in quadrants 2 and 4. So 6 pi over 6 minus pi over 6. What, we're looking at 5 pi over 6? For one of my answers. And quadrant 4, 2 pi over 6. 12 pi over 6 is the same as 2 pi. So we're going to go back pi over 6. So the other answer would be 11 pi over 6. 11 pi over 6. Okay. All right. That's example 5. 4 we have to do yet.